Okay, all right. So let us start today's session. This is session number 10, and today we are going to discuss the line inductance calculation. And so first we will see this what are the four steps to calculate the line inductance, and these are the four steps for calculating the line inductance. First, we need to calculate the magnetic flux intensity, and that is done by the Ampere's circuital law. And then we will find this magnetic flux density using the expression magnetic flux density is equal to permeability multiplied with the magnetic flux intensity, that is B is equal to mu H. And then we will find this flux linkages L, that is we will see that how can we relate this flux density and the magnetic flux linkage depending upon we are finding the internal flux linkage or the external flux linkage. And fourth, we will and the last one step is that we will finally get the inductance from the flux linkage per ampere, and this relation is L is equal to flux linkage multiplied with this current. So, if we find the total inductance of solid cylindrical conductor, then we have to calculate both the internal inductance and external inductance. And for finding both these, we will first find the flux linkage, internal flux linkage and the external flux linkage. And for doing this, so we have some assumptions. So that will make our calculation simpler. So assumptions are that we have to consider that conductor is not means long enough that end defects are neglected, and the second is that we are considering the conductors as non-magnetic material, and so that this permeability will be 4 pi into 10 to the power minus 7, that is the air permeability. And we have also considered the neglecting the skin effect, that means this we have uniform current density throughout the conductor. A skin effect is neglected means we have considered that this current density is uniform throughout the conductor, and this relation H tangential dl is equal to I enclosed, that is the Ampere circuital law. So we will apply this Ampere circuital law to get the magnetic flux intensity. So let us see the first case, that we are going to find the internal flux inductance. So for finding internal flux inductance, we can use the Ampere circuital law, that is Hx into 2 pi x over the distance x. We will write this expression first, that will be the current enclosed for this distance x, for the radial distance x, and where x is less than radius r. And the second expression is that how much amount of current we can get at a distance, at a radial distance x, by using this expression. I is the total current flowing through the conductor, and x is the radial distance over which we have considered this, which we have considered this circle. And we will get this relation, and when we put this Ix is equal to I into x divided by r square for a solid cylindrical conductor, we will get this Hx is equal to xi divided by 2 pi r square. When you put this second expression Ix in the first expression, you will get this Hx. Now we know that V is equal to mu naught H, so that we will get the magnetic flux density over the distance x, and we will get this expression. Now we will find the flux. For finding the flux, we know that phi is equal to magnetic flux density into the area. So area we have considered length as 1 meter. Therefore this dx will be width. So area will be the 1 into dx. Therefore phi d phi will be bx into dx Weber per meter. And flux linkage consecutively you can find on putting this relation x divided by r square d phi. You will get this expression, and finally you will get the internal flux linkage by integrating this d lambda. So you will get internal flux linkage at half into 10 to the power minus 7 into I Weber turns per meter. And we know that L is equal to lambda I. Lambda internal divided by I. Sorry.
lambda by I.
Yes, sorry. Lambda internal divided by I. So we will get this internal inductance of a solid cylinder conductor. So here you can see that this is independent of the radius of the conductor. So this is very important point. Examiner may ask this question directly in one mark question, independent of radius of conductor. Now we will see the external, how we can find the external flux and external flux linkage, and from there we can find the external inductance of solid cylindrical conductor. And for that we have this is we have considered the 2 points d1 and d2 at a distance d1 and d2 from the core of the conductor, and we can write this expression in the similar way as we have written previous. And here we hx we can directly write ix divided by 2 pi x, because this, so you can get this expression, it will cancel out 2 pi with this 4 pi, then you will get 2 pi into, sorry here is a mistake, here it will be 2 into the 10th power. So you will get this expression, and from this you will get the flux for infinitesimally small distance distance we will get the flux linkage, and you can get this expression d phi is equal to bx dx for a for a length of 1 meter. And if we write this flux linkage with respect to flux linkage at point 2 with respect to first point, then you will get this expression 2 into 10 to power 10 minus 7 I L d2 divided by d1 Weber turns per meter. Now if we consider the first point, that is first reference point d1 as the outer, at the outer of this conductor, so it is a distance r from the core of conductor. So you can write external flux linkage at 2 into 10 to power
Sir,
minus 7. Yes.
sir, here we take a limit d1 to d2. Sir, I didn't get it.
So this is the, like we have whatever the reference point you have considered. So we have to integrate with respect to some point. So we are integrating with respect to d1, that is at distance, means we are integrate at a distance d1 from the core, from the center of the conductor. And if we take this d1 as the radius of conductor, then it will come as d2 divided by r. It is coming from the integration of this flux linkage d lambda. So this is for understanding,
Okay, sir.
because we have to consider the we are calculating the external flux linkage. So we could not take inside the, we could not take the point inside the conductor, we have to take the point outside the conductor. So
Sir,
in this,
then we can take, sir.
in the previous we have for consider 0, because we have considered the first point as the center of conductor, right?
Yes, sir. Then, sir, we can take from r distance to d d2.
Directly.
Okay.
Yes, you can take directly also because we are finding the external flux linkage. So we have to take the point outside the conductor.
We can take from radius of the conductor also.
Yeah, that's correct. And you can correlate with this previous how we have found this internal flux linkage. We have taken the point at
0
first
to
point center of the conductor and the second
cent
point at the radius because this
radius of
radius
conductor.
radius is the boundary line for internal and external flux. So therefore you will get this total flux linkage like this. So here you can write.
Sir, but when we calculate the external inductance, then we take from radius of R to point where we want.
Yeah,
Okay, sir.
so half into, we can write half as 2 into ln e to the power 1 divided by 4. So you will get this expression. And external, we have external flux linkage at a distance d, we can write like this, and then we can get the total flux linkage. If you just sum up this all, this ln will get add up, inside the term of ln will get add up. So we can write d divided by r dash, where r dash is e to the power minus 1 divided by 4 into r. So this is very important, that is 0.7788 r. And this inductance at point P, external point, that will be 2 into 10 to the power minus 7 ln d divided by r dash Henry per meter. Very important these points, this expression. So I have derived this inductance for the solid cylindrical conductor for a single conductor. In the similar way, you can define the other complex inductance calculation. So I have not derived all these derivations here, but I have write the summary points. So important expression like total inductance due to solid conductor at distance d will be 2 in 10 to the power 10, 2 into 10 to the power minus 7 ln d divided by r dash Henry per meter. And similar, a single phase having two wire system, one in one wire it is current is going, and in through neutral wire current is coming out. So for this we can just sum up the inductance of both the wires. You will get multiplied by 2 in the first expression, that is 4 into 10 to the power 10 minus 7 ln d divided by r dash Henry per meter per circuit. So in this single phase two wire system, examiner may ask about this only single conductor. Then you have to use the first expression only, this expression. If they asked about this total inductance, that is per circuit, then you have to multiply with 2, right? And now this three phase three wire with equal spacing, this you will get the same inductance expression as for the single solid conductor. 2 into 10 to minus 7 ln d divided by r dash Henry per meter, that is for a single phase, per phase, like for a phase, b phase, c phase, all are equal. And we have considered the symmetrical spacing or equal spacing. So let us solve the first problem. So the first problem is that we need to calculate the line inductance per phase for a balanced three phase 60 Hz transmission line with a conductor geometry of an equilateral triangle with distance is equal to 5 meter and radius is equal to 1.24 centimeter. And this generally we this conductor is called a rook conductor and a length of 5 miles. So all of you try, and whoever is getting answer, type your answer in chat box. So we know that this three phase, the inductance per phase for three phase system. So these are symmetrically spaced with each other, and given that equilateral triangle. So what are the things given? All the conductors of a three-phase system are displaced with each other at a distance of 5 meter, and radius is given at 1.24 centimeter. So we need to find r dash, that is effective radius. We have seen in the expression we have to use 0.7788 into r. So we will use this in the final expression. This will be 0.0124 meter. Suppose this is A phase, conductor for A phase, B phase, C phase, and all the inductance for each phases will be equal to each other. So we will find the inductance for phase A. So we will use this expression 2 into 10 to the power minus 7 ln d divided by r dash Henry per meter. And some, I also want to mention here that many of you use this one also, 0.2 into ln d divided by r dash milli sorry milli Henry per kilometer. So what, just remember one expression. If you are remembering this expression, that is also fine. But just know what the question has been asked in which unit, Henry per meter or milli Henry per kilometer, whatever you can get that. And in some textbook you may find that they have calculated the inductance expression in the terms of log in place of ln. So just be careful. You know how we can convert the ln into log and log into ln. So just remember the one expression, and this expression is easier than log expression. In log they have taken the base as 10, and here we have taken ln, that is base is e. So in this problem nothing is there, just you have to put the values, and this d is 5, 9.657 into 10 to the power minus 3. R dash will come like this. You will get 2 into 10 to the power minus 7, 6.25, that which 1.25 10 to the power minus 6 Henry per meter. So if you write in millihenry per kilometer, then what will come? Can anyone tell? Anil, Vargavi, Ritesh. If you want to write this answer in millihenry per kilometer, how can we write? Anil,
Yes, sir.
what will be the answer in millihenry per kilometer? So if you see that, if you write in terms of kilometer, then 10 to the power minus 3 will come out. So here it will be Henry per kilometer. and again 10 to the power 3 will go into this, so it will be 1
1.25 millihenry by kilometer.
yes, 10 to the power 10 to the power minus 6 is constitute millihenry per kilometer if you convert into henry per meter into millihenry per kilometer. So till here any doubt? So
No, sir.
let us move to the next part. So now we will see this bundling of conductors. So generally we can see the bundling of conductors if you travel like through train or highways wherever, because this transmission line generally we see in the outer field area. So there we can see this bundling of conductors very easily in transmission lines, and these are very is commonly used, and all over transmission lines are using this bundling based on the voltage rating. Whatever the voltage means higher the voltage, more the bundling will be there. And why do we the bundling? To just to increase the capacity of high voltage transmission lines. And it is very common to use a number of conductors per phase. This is known as conductor bundling. And the typical values for the two conductors are 345 kV lines. If 345 kV line is there, they have to use two conductors per phase. And for 500 kV, they have to use three conductors per phase. And for 765 kV, they are using four conductors per phase. And they may go beyond that, but this is typical values. And we are increasing the capacity of high voltage transmission line, that also leads to increase the GMR, geometric mean radius. We will see that how we can find this geometric mean radius, and this by doing the bundling of conductors it increases the GMR, and this GMR that leads to many good means like that are beneficial for us. Like first it reduces the line inductance, and by reducing the line inductance it reduces the corona losses, and the line drop will be also less. And this also reduces the surge impedance, because surge impedance is equal to under root L divided by C. So it is reducing the line inductance, therefore it is also reducing surge impedance, and it also reduces the radio interference. So bundling of conductors has many advantages, and this is very like many of a student also get confused that this is the different phase. No, this is single phase, and these are all having the same voltage. Like for a single phase, they are all bundled, so they are having the same voltage. Now we will see the different configuration of bundle conductors, like for two conductors, three conductors, and four conductors. They are general configuration for bundle conductors, and how we can find the geometric mean radius of these conductors. So for two conductors, we will use this geometric mean radius is equal to r dash into d, and whatever the number of expression inside the bracket, that will be the under root, like 1 divided by 2. The number of terms inside this bracket is 2, so it is 1 divided by 2. In similar way, we can find the geometric mean radius for three conductors, r dash into d into d. So there are three terms inside the bracket, so it will be 1 divided by 3. And for four conductors, there are four terms inside the bracket, so it will be 1 divided by 4. So here we have three conductors, one, two, three. So suppose we are finding the geometric mean radius of one conductor. Then it is first we will consider this effective radius of first conductor. It is having radius r. So it is having radius r. So the effective radius will be r dash, and d is the distance from this other conductor, that is d, this distance from the second conductor, and d the distance from the third conductor. So in this way you can find the geometric mean radius for three conductor configuration. Now for four conductors, like suppose this is conductor number one, this is two conductor, three conductor, fourth number conductor. So for suppose we are finding this geometric mean radius for first conductor, and so first we will write the effective radius for first conductor and the distance of this conductor one with respect to other conductors in that bundle. So the second distance of second conductor with respect to one will be d, and third conductor will also have distance at a d, and fourth conductor how much this distance will be there. What is the distance of this one?
under root 2d.
Yes, under root 2d. So this will come into, so there are four distances inside the bracket, so it will be 1 divided by 4. Here you may wonder that we have taken this GMR for whole bundle, and we are telling you that this is for one conductor. So if you find that like suppose if we are taking the example of these three conductors, so GMR for first conductor and GMR for second conductor and GMR for third conductor will be equal. So if you take the whole GMR, that will be GMR1, GMR2 and GMR3. So this is also equal to GMR1. That's why we are taking this, writing like this directly. No need to go these basic points. If there are unequal distances, then this is useful because this geometric mean radius for first conductor is different, second conductor is different, third conductor is different. This is symmetrical configuration, so we have to we can write the geometric mean radius directly here. And in this for bundle conductors also, we will use the same expression for finding the inductance per phase, that will be 2 into 10 to the power minus 7 ln GMD divided by GMR Henry per meter. So the question is similar to the previous problem, but here in this problem we have considered each phase has four conductors in a square bundle. So you have to calculate the inductance. And other things are same, like that all phases are at a distance of 5 meter, and each conductor has radius of this one, but each phase has four conductors also in a bundle, in a square bundle, and this bundle are 0.25 meters apart. So now you need to find the line inductance, and we will see the benefits here, how we will get this geometric mean radius, uh, how this increases geometric mean radius, and subsequently it reduces the line inductance. So this figure you can write, make like this. So each phase has four conductors, like this is A phase, and they all are symmetrical spaced, that is they are in equilateral triangle, and this is B phase, C phase, and this is B phase, C phase. So if you see the distance between each other in a bundle conductor, between the bundles, that is 0.25 meter, and this distance like between A to B phase and B to C phase, how much this distance is?
5 meters.
Yes, 5 meter, correct. So this is 5 meter, and we will first find this geometric mean radius. For geometric mean radius we have to find the effective radius of a conductor. So R is given for each conductor is 1.24 centimeter, that is 0.0124 meter. Therefore, we will get R dash 0.7788 into R, that is 0.0124 meter, that will be 9.65 into 10 to the power minus 3 meter. Now geometric mean radius of each conductor, like whole system, you can say, because all are identical, therefore geometric mean radius will be r dash 0.25 into 0.25 into 2 root 2 into 0.25. And how much right here? 1 divided by 3 or 4? Can anyone tell how much I should write? 1 divided by 3 or 4?
1/3, sir.
Vargavi,
Yes, sir. Out.
Anil,
Yes, sir. 1/3.
how will write 1 by 3?
Uh, be-
We are
because
finding
you are taking A, B, and C.
A and B, C, we are finding for bundle conductor, geometric mean radius of bundle conductor. And I have
Mm.
already told you that you should see the number of turns inside the conductor. So, like we are finding for bundle conductor, this is like bundle conductor, like 4 conductors in a square bundle.
1/4, sir.
Yes, a square bundle. So 1 divided by 4. So this is for one conductor R dash, and other conductor all are displaced by 0.25 meter, 0.25 meter, and this is uh, diagonally distance we will root 2 into 0.25. So here you will get geometric mean radius of bundle conductor, that is coming as, you do simplification, 2.134 10 power minus 4, 1 divided by 4 is equal to 0.12 meter. Correct. Means geometric mean radius we always find for the same current, like, and we will go for geometric mean distance, then we will find for the conductors in which other currents are flowing, and in this bundle conductors the similar current is flowing in all the conductors, means whatever the current is flowing they all have the same current. So here we will write this like inductance value for bundle conductors also same, three phase system is there. So ln d divided by gmr Henry per meter. This will be per phase. In this question is also asked about the inductance per meter. So this is 2 into 10 to the power minus 7 ln d will be 5, 0.12 Henry per meter. This will be 2 to 10 to the power minus 7, 3.73, that will come up as 7.46 into 10 to the power minus 7 Henry per meter. Answer. So in the last problem, if you see here, effective radius is 9 point, this r dash is 9.657 to 10 to the power minus 3 meter. And now here see, this is approx 10 times bigger that we are getting earlier. 9.67 to the power minus 3, it is approximately like we can write here also. How much you can write? 0.009, that is approximately equal to 0.0113. Yes. So here you can see that this GMR, due to bundle conductors, GMR increases 10 times, 10 times bigger due to bundle conductors, 10 times bigger due to these bundling of conductors, and inductance value will also get increased. In the previous case we have got 1 point, sorry, this 1.25 into 10 to the power minus 6. Here we see how much this also get increased. Sorry, this will reduce, inductance will reduce, sorry, this is reduced also. GMR will increase because GMR is a denominator side, so inductance will reduce. So this reduces from the previous case by bundling conductors. Any doubt in this problem? Bhargavi, Anil, Ritesh.
No, sir.
Okay, fine. Now let us see the some gate problems also. So this problem is asked in 2022. So if you see our university exam syllabus, then inductance calculation is very big. But in GATE, they don't ask very complex problems. Generally, whatever I have seen, they ask the basic problems which you can calculate easily. That are not very complicated solution. That are not very complicated type that mathematical expression. So this is asked in GATE 2022. If you know the basic of inductance calculation, then you can easily find the answer for this problem. This is very simple, so it is asked in 1 mark problem. So here you have to find the geometric mean radius, and this is a stranded conductor having 4 equal strands with each a strand of radius r, and shown in the figure below is. So you calculate, all of you. We have seen about the bundle conductors. So similar expression we will use in a stranded conductors also. Geometric mean radius of a stranded conductor, how you can write? We will write for this first conductor, then this is suppose like first conductor, second conductor, and third strand. Better because they are touching with each other, so we used to call it as a strand. So first strand, second strand, third strand, fourth strand, and the distance is similar way you can write. So from the second strand is from 2r distance, and third strand is also 2r distance, and this is diagonally related, so this is 2 into root 2r. Just you need to put all these value, r dash into 2r into 2r into 2 root 2r, and the power will be 1 divided by 4, because whatever the number of distance inside the conductor, it will be the 1 divided by that number of distances. So 1 divided by 4. Therefore you can write 0.7788 into r into 2r into 2r 2 root 2 into 2 root 2 r 1 to the power of minus 4. So take r outside. So inside it will be 0.7788 into 8 2 root 2 1 divided by 4 r, that will be 8.811 1 to the power divided by 4, it will be coming as 1.723 r. So correct answer is D. Any doubt? Any doubt? Bhargavi, Anil, Ritesh?
No, sir.
So I have one question here. So what type of conductor generally we use in this high voltage transmission line? This is related with the standard conductors and this. So what type of conductor we use? Have you heard the name of ACSR?
Yes, sir.
That we use.
Aluminum coated steel reinforced.
Yeah. So this conductor we use in the high voltage transmission line. Aluminum conductor is steel reinforced. That is not coated conductor. Aluminum conductor is steel reinforced.
Yes, sir.
Now let us come to the next part. Now the next part is that we have seen the bundle conductors, we have seen the inductance calculation for single phase system, three phase systems, and now we will see the transmission tower configuration that is unsymmetrical. How it is unsymmetrical? So the problem with the line analysis we have done so far, that we have assumed the symmetrical configuration, that all phases like A, B, C are symmetrically placed with each other. That is we have considered. But such a tower configuration is seldom practical because due to some mechanical constraints they are not equally placed with each other. That therefore in general we cannot say that all the conductors placed in the three phase systems are equally placed with each other. So we have to do something such that there will be balance system. If these are not balanced, then what happen is that whatever the voltage you apply at one end, due to different inductance, because due to different inductance for each phases, that will lead to different voltage drops, and finally you will get the unbalanced voltage at the output. This is the problem. If this is not symmetrically spaced with each other, all conductors are not symmetrically spaced with each other, then whatever the voltage you apply at the sending in, due to this different inductances values, you will get the unbalanced voltage at the output. So we have to do something so that we will get the balanced voltage, and all the inductance for each phases are equal. So there is the concept comes as, do you know what that concept we call?
Transposing.
Yeah, very good. Yeah, you are Anil.
Yes, sir.
Yes, very good. Transposing of conductors. This is very this you can see this station where this transposition of conductors have been applied, like for a distance, and we divide the distance into equal parts, and for each part each conductor have to place at that place. Like for this part a phase is at the top, so for the other part it will be placed at the second place, and for the rest part it is placed at the third place. And therefore all the phase will have the same experience, means all are placed at each other place, and finally we will get the same inductance for all the conductors, and that leads to the similar inductance for all the phases, and we will get the balanced output voltage here also at the output side. So I have written down here that what is the transposition of conductors, and to keep the system balanced over the length of transmission line, the conductors are rotated so that each phase occupies each position. This point is very important. Each phase occupies each position on tower for an equal distance. This is known as transposition of conductors. And for transpositions, for transposed conductors also, this expression is coming because we are doing that. Why we are doing the transposition due to balance system also, to doing the balance. And if you are doing balancing the system, that means the inductance for each phase will come equal. So that's why we are get on averaging the inductance for each phases. In after doing the transposition, you will get the similar inductance expression. So the inductance expression is similar to whatever we have seen earlier. L is equal to 2 into 10 to power minus 7 ln GMD divided by R dash Henry per meter per phase. And suppose this each conductor is bundle in nature. So this R dash will convert into GMR. So in the place of R dash, you have to use the geometric mean radius for the bundle conductors, and you will get the transposition line with bundle conductors. You will get the expression L is equal to 2 into 10 to the power minus 7 ln into GMD divided by GMR Henry per meter. That is for single phase. So any doubt? Now we will see the next problem. And this problem all of you try and type your answer in chat box if you are getting the answer. And the problem is that a three-phase 50 Hz transmission line consists of three equal conductors. So three equal conductors are there of radii r, each having radius r, each having radius r, placed in horizontal plane with a spacing of 5 meter between the medial and each outer conductor as shown in figure. Determine the inductive reactance in ohm. We have to find the XL. We have to find the XL. Per phase per kilometer of the transposed line. Here transposition is also given if the radius of each conductor is 25 mm. So don't afraid with transposition, it is nothing. It is used to just balance the system. So transposition is we are using for balancing the system. That means inductance value will be similar. We will use the same expression. That expression is L is equal to 2 into 10 to the power minus 7 ln GMD divided by GMR Henry per meter. So we need to find GMD, GMR, and here bundled conductor is not there, so we will write effective radius R dash. Why to need to write GMR? So R dash for each R effective radius of each phase will be R dash is equal to 0.7788 into R. So that is 0.7788 into 0.025 meter, because radius is given as r is given as 25 mm. 25 mm is 25 10 to the power minus 4, so 0.0, sorry, 10 to the power minus 3 meter. So this is the r. Now we'll find the GMD. So I just want to hear from you, what will the GMD? Anil, Bairagvi, anyone can say?
25 mm.
GMD.
5
GMD.
5 5
Yes, 5 5, and then
5 10
yes,
1
right.
by 3.
Yes. So how this GMD come? GMD comes from, we will take the distance with respect to each other, DAB, DBC, in which the conductors are means currents are different, DCA, that is the GMD. So we have calculated GMD and R dash also. So if you write this GMD value, then it is coming as 6.2996 meter. Therefore, finally, we can write L value 2 into 10 to the power minus 7 ln GMD 6.2996, R dash is 0.7788 into 0.025 Hindi per meter. So you will get, if you are facing any problem, then you can ask here. So 2 into 10 to power minus 7, 5.78 Henry per meter. That is 11.56 into 10 to the power minus 7 Henry per meter. And in this question, it is asked about per kilometer, per phase per kilometer. So we will convert this into per kilometer. So 11.56 into per kilometer, 10 to the power minus 4, 10 to the power minus 3 will come out. So Henry per kilometer, and we need to find this reactance. So XL will be omega L,
Omega L.
correct. So 2 pi FL 11.56 into 10 to the power minus 3 4 ohm per kilometer. So that is 3631.28, 10 to the power minus 4 ohm per kilometer. If you write in this way, 0.363 ohm per kilometer. So the answer is 0.363. And now let us see the next problem. So I have solved this problem in the first session only. So here I have directly written down so that you can just recapitulate, just revise all the problems, because there I have gone very fast, and here we are going slowly to each part. So I have just written down all the problems we have solved in the first session. So quickly you can go through this question. In this question, similar expression you have to apply, and GMR we all know that R dash we can write it because uh, there is no bundle conductors, and this GMD or in GMR will change in case of bundle conductors also, and in this double circuited line. In double circuited line, generally we do for increasing the reliability of system. So in general, I have not seen question on double circuited line, but in there also GMR will get changed. And bundle conductors we have seen problems here, and GMD we can found in similar way. So GMD all the distances are equal, so it will be 1 meter only, and this is symmetrically spaced, so directly you can write one distance, no need to calculate this GMD like this. And then in the last case, these distances are unequal, so we have calculated by this way. So therefore you can get this line inductance value, and finally you will get this XL. So this is similar problem we have seen in the last. So this is for GATE 2017, and it is of 2 marks. See, the inductance calculation are very simpler, and you have to just apply the expression, this expression only. And the next problem is asked in GATE 2015. It is also up 2 marks. It is little bit older, so that's why it is asked for 2 marks. But if this question asked in nowadays, so they will definitely asked in 1 mark question. So In this, we have seen like this type of problem, a composite conductor. This is like bundle conductor only. So here it is of composite conductor is given. So three conductors are bundled. Three conductor radius R is the radius are arranged shown below. So you need to find geometric mean radius. This is given, so you need to find K. So this is very simple. All of you know how to do this problem. And now this problem is asked in, I think, GATE 2015 only. So this is asked in GATE 2015, and it is for 2 marks. It is little bit calculative, but you can calculate. In this question, you have to, there is relation given between the inductance for single phase system and three phase system. And if you see in this question, see that the inductance per conductor. So it is mentioned that inductance per conductor of the single phase system. So we have found, we have not multiplied with 2, that we have taken the first expression only, 2 into 10 to power minus 7 ln divided by r dash Henry per meter. So that is the thing. And for three phase system, we will find this. It is given that positive sequence inductance per phase. So for per phase, we know that is same expression whatever we use for the single phase per conductor. So we will use this expression, and we can calculate this GMD and GMR. So here this GMD will be different because we cannot write the D distance because because all are not equally placed with each other. Here one conductor is placed at 1 meter, another conductor is placed at D distance. So you have to calculate GMD, and this R dash GMR, you all know that GMR is same, all conductors are similar, all conductors of same radius, so you can calculate R. And there this L3 phase relation is given single phase 1.055 L15. From there you will get the D distance. In this problem it is asked about D. So all of I questions that have been asked in GATE we have discussed. Moreover, I think I have discussed about the inductance calculation. And in the next session, we will see the problems based on the capacitance calculation. So that's all about today's session. You may ask question if you have. Thank you for attending this session. Vargavi, Ritesh, you have any doubt or any concern, you can ask.
No, sir. Thank you, sir.
Okay. Okay. Thank you, everyone. I am closing this session.
Thank you, sir.